Hello and welcome to MatheMARKicks Tutorials Episode 3. Alright, and I apologize for uploading this a bit late since I'm still figuring out some things in order to improve my tutorials. And moving forward, we're going to talk about concept of logarithms, which is kinda introduced during the last episode, but today we're going to dig deeper in learning about logarithms in order to understand more some exponential functions concepts. Specifically, we're gonna talk about the nature of logarithms and their properties that you may use later on in solving exponential functions, equations, as well as logarithmic functions and equations. So, look at the table, and it's easy to solve for the value of x in the first two rows since both 10 and 100 can be expressed in base 10. We all know that x equals 1 in the first row since 10 raised to 1 equals 10. So therefore, x here is 1. As well as 10 raised to 2 equals 100. That's why in here, x is equals to 2. But what if 10 raised to x is equals to 55? We all know that it's between 1 and 2. But then, how do we find the exact value of it? Since 55 is in exactly between 10 and 100, do we just assume that x is equals to 1.5? Let's see. So, same rule applies when there's exponential functions and logarithmic functions. And you can write exponential equations in logarithmic form. So, from b raised to x equals n, it becomes log of n to the base b is equals to x. So that's how you read it. So the base becomes the small number here, and then the small number here, exponent, becomes the one that is isolated in one side. And then what's left is the number, so it's here together with the logarithmic operator. So same rule applies again for b, x, and n respectively. Now let's try solving for this logarithmic exponential equation by using logarithms. So we can write 2 raised to x equals 64. Sorry, that's a 64. And then log 64 base 2 equals x. You may use your calculator. You're getting x equals 6. What if we use exponential equations? 2 raised to x equals 64. 2 raised to x, expressing 64 in terms of base 2, it's 2 raised to 6. Therefore, x equals 6. Later on, we're gonna deal with properties that you may use in solving. Okay. Next one. Let's use the example earlier. 10 raised to x equals 55. So, let's write it in logarithmic form. So, the exponential equation becomes log of 55 base 10 equals x. You may interchange the two so you will be more comfortable with the variable at the left. So you may write your answer in that form, or you may use your calculator to get the decimal value, which is approximately 1.74. So as you can see, it's not equal to 1.5. Okay. Moving forward, we're gonna deal with the notations As you can see, there's a table here with the corresponding x values and the resulting n values. As x increases, you substitute it to the formula. The n values arrive at this common number, quote unquote, which is 2.71828, which is also known as the Euler's number that is associated with the natural logarithm, or LN. This is more on the calculus side of proving, and we're not gonna tackle about that one here. So as mentioned, it is the natural logarithm. It is when the Euler's number e is the base. You can write it as simply ln of the number, which can be pronounced ln as ln. The common logarithm is when the base is 10. You can opt to not write the number 10 in the base and simply write log. So these are the two notations. If the base is not 10 or not e, then you must use the standard form as shown in the previous slides. For today, we're going to talk about also the properties, and one of the properties is the product law as shown here, wherein two logarithms are added with the same base, which is combined with the product of those two numbers, the big numbers here, m times n, combined in a single logarithm of the same base. Now, how do we prove this thing? So, we let the expression log of m base b equals x, and then log of n base b equals y. Expressing each into exponential form, the base b exponent x equals the number m. And then same thing here, b raised to y equals n. If you're going to multiply them, mn is equals to b raised to x times b raised to y. By applying the properties of exponential equations, b raised to quantity x plus y. And then you may express this mn equals b quantity raised to quantity x plus y into logarithmic form. So it's log of the number mn base b equals the exponent x plus y. And then you may write x plus y, revert it back. So therefore, this is x becomes log of m base b, and y becomes log of n base b. Now you've proven it. Okay. This is the proof for product law. There are more properties such as the quotient law, which is simply the opposite of product law. Instead of addition, it becomes subtraction right here. And then when you combine them, instead of multiplication, it becomes division. For zero and identity laws, it's simply when the number is 1, any base, but the number is 1, as long as the number is 1, the answer will always be 0. This whole thing becomes 0. If the base and the number are the same, let's say log of 10 base 10, it's always equals to 1. Or in general, log of b to the base b. You may use the concept of exponential equations and expressions to prove this too. And I challenge you to prove the quotient law. For the power law, if the number here is raised to the exponent here, the little exponent of this number is the coefficient in the other side, and vice versa. Do take note that what you're raising here is only n, not the whole expression. That is one of the misconceptions. And using some of the laws presented, can you try to prove and show that log of log of b raised to x to the base b is equals to x? I will wait for that. And that's all actually. And thank you for watching, and I hope you learned something new today. And we're gonna talk about logarithmic equations after. So stay tuned and thank you so much.